Okay, well, let's go. Well, Masumi is not here today to introduce the colloquium speaker, so I'll be doing it. Today's speaker is Alin Parashiv. And Alin got his PhD from Monash University in Australia in 2018. There, he focused on observations and interpretation of small-scale flaring and eruptive activity. After his PhD, Alin moved to, as he calls it, beautiful Boulder, as a postdoctoral researcher at the National Solar Observatory. And there he gained experience in infrared observations and coronal magnetic field inferences and inversions. Alin is currently a postdoc at HAO, also in Boulder, where he enjoys learning about spectral polarimetry and working with students on solar-focused observations, inversions, and machine learning applications. And today, his talk is on the topic of inverting coronal vector magnetic fields from infrared polarimetric observations. So I'm going to give the floor to Alin.
Thank you, Rebecca. So, the main idea of this talk is to present an inversion algorithm that I started to develop it at NSO, and I am continuing to work on it due to the generosity of HAO funding me for a while longer. And it's about using infrared polarimetric observations and trying to infer full vector magnetic fields from them. A task that's proved quite elusive, and it's more like a holy grail. And let's start with the main ideas of why would we want to do that. So what would coronal inversions be applicable to? One would be the nature of waves and their turbulence effects in the corona. These have been studied in the higher corona for a long while, and even going back to the Ulysses missions. But proving and trying to describe their sources has been quite elusive, and there are only a couple of, to my knowledge, only a couple of comp observations that managed to try to probe the sources of waves propagating through the entire heliosphere. Of course, the more classical application of coronal magnetic fields is diagnostic of off-limb magnetic structures like streamers, cavities, CME arches, and post-eruptive arches, and so on, even before, during, and post-eruptions. And these efforts that we've been working on might actually revitalize theoretical studies on coronal polarization, which are have winded down a little in the past because there's not that many actual coronal full Stokes coronal observations to work with. So let's start with some definitions that will be useful throughout this work. So starting with simple things, I will use the following convention for directions. So the X component is the component that is normally integrated along your sight in an observation, and you don't see it. Y component is taken in the east-west direction, and the Z component is taken in the north-south direction. And there are a couple of more complicated angles and definitions here, but I'm not going to torture you with those. And in terms of physics, we need to define a couple of things. First thing, usually the corona is well approximated when probing the Zeeman effect within a strong field approximation. For people who don't know, the Zeeman effect is the splitting of atomic lines in the presence of a magnetic field. Very important to this problem is the atomic alignment factor. And what is this? So when you have an atom floating in the corona, it's not just freely floating in a soup. It's bombarded by radiation in an anisotropical way that aligns it in a certain direction. Now, any exterior magnetic field, and this is called atomic alignment, and any exterior magnetic field influence will alter that alignment. And this is a powerful diagnostic that we will employ. And another more observational constraint is that we need to target very strong coronal lines in the infrared, because the polarimetric accuracy is not that good. So before going into the complicated part, let's talk a little about what infrared spectroscopy at 1000 to 5000 nanometers or 1 to 5 microns is. So we started from the cryoner specification, as this project was initially suited to recover information using the Dickeys cryoner instrument. We selected 4 ions of interest for which we can produce inversions. And these are the iron 13 line pair at 1074 nanometers and at 1079 nanometers, the silicon 10 line at 1450 nanometers, and the silicon 9 at 3934 nanometers. And what I'm showing with these plots is just a sample of a full polarimetric observations with Stokes IQ, and V, created as correspondent to a small telescope. And here we can see the main problem that coronal polarimetry has been faced with decades. A small instrument will not be able to recover the circular polarization component, that is Stokes V, in a normal observation, and it will be just be drowned by noise. So normally you would need about a signal to noise ratio of 10 to the 4 counts in I over V to start recovering meaningful Stokes V signal. And this has been a problem, and Dickeys is advertised as the first instrument to be capable of resolving that. Okay, wait, this one. Okay, this part is, I'm gonna shamelessly present this part. It's not my work, it's my fantastic REU student work at IA, and it directly relates to the problem in question. So we started to analyze the spectral region that for the 4 selected coronal ions, and we we frame those data in spectral windows that are compatible with cryoner's slit wavelength range for each of the specific ions. Then, via the courtesy of Kevin Reardon, we found an atlas from the McMath Pierce telescope of atmospheric absorbers in the regions of interest. And we overplotted and we synthesized coronal emission using the coronal line emission code CLE that was developed by Phil Judge and Roberto Cassini. And we overposed these lines over the atmospheric absorptions. We also, importantly, we also scoured the literature for any measurements of the intensity of these lines with respect to the background. It was hard, but we could find a few measurements corresponding to each of the lines. And you will see that some are more problematic than the others. You will get good signal to noise ratio in, for example, in the iron 1074 and in the silicon 101430, but the silicon 9 is very weak when compared to the background. Of course, Dickeys might do a good job, a better job in the future, but that's to be seen. Okay, then we also analyzed the influence of any spectral shifts in those lines on what you will recover in these spectra. So, and compared with the atmospheric absorptions. And this is needed for 2 reasons. One, to find a way of automatically resolving Doppler shifts and so on, and quantifying them properly. And you can see that in some particular cases, a standard Gaussian-like fitting for the line profiles might not work. So some more sophisticated fitting using statistics is needed. But more importantly, a more deeper atmospheric lines might actually will cut from your Stokes signal in especially for shorter exposures. And that might prove a problem if you want to do extremely fine polarimetric ratios, which I'll get to. So these are the correspondent plots for Doppler, for reasonable Doppler shifts in the middle and for extreme Doppler shifts in the order of 3 to 400 kilometers per second in the extremes. For this is the iron 13, 1074, 1079, and the upper and bottom plot are the just a scaled intensity and an intensity based on older an actual intensity based on older observations. More to it, more on this. These are the silicon 10 and silicon 9s, and we only have a panel of silicon 10 because the observed intensity ratio was found to be 2, which was also our randomly chosen scaling factor. But again, I draw attention to the fact that silicon 9 will prove to be very problematic, especially since it's hidden inside the molecular absorption band of, I think this is nitrous oxide or something like in the atmosphere. So what will these things help us with? This is also a full spectroscopic output for the 1074 line at rest wavelength, and with all the atmospheric lines identified, absorptions. And because the McMath-Pierce Atlas had even higher resolution than what the cryoners will be able to perform, we also convolve the data with respect to the cryoners resolution to see if our atmospheric identifiers are relevant or not in context of an actual observation. And at the end, you get a table such as this that lists a useful line of both atomic and molecular. So it's both atomic lines from scattered photospheric lights and the telluric molecular lines that can be used to Doppler calibrate your coronal emission and make sure you're actually properly integrating polarimetric signal out of it. And so Atia just got her first paper accepted, and it's up on arXiv, and it will be available imminently on the publisher's website. And I'm really proud of her and her achievement. Okay, next part. Still not getting into what CLEDB does. We first need to talk about some geometry and symmetries native to the problem. So the problem of coronal magnetometry via spectropolarimetric techniques has been incrementally developed by Cassini and Judge 99, Ploman 2014, and Dima and Shad 2020 being the most important works here in my opinion. And especially important today is the Dima and Shad paper that offer a purely a vector magnetic field analytical solution to the problem. And what they did, they computed an atomic factor which they called F, and showed that if you use line pairs from the same ion, like for example the iron 13 1074 and 1079 atom, where both where this F factor will yield zero in both cases, you will not be able to recover the line of sight orientation of the magnetic fields, as the sign will be the analytical function based on the sine square of this theta b angle will be undefined. So this is a degeneracy, a fundamental degeneracy in terms of purely analytically expressed solutions. And the other solution here was to replace one line with a counterpart that doesn't have an F equals 0. But for our problem of hand, a line combination with one not having F equals 0 would imply using multiple atoms, and that opens another different can of worms. And so in the end, the analytical solutions with such a purely analytically driven inversion will still be degenerate in sets of 4 based on the line of sight degeneracies. So so our goal became to figure this out and see if we can actually recover routinely vector magnetic fields in the corona, or we should just be content with line of sight fields, and that should be it. And we took two approaches here. Firstly, we collaborated with some friends in Sweden and an atomic group, and we computed large-scale calculations of Lambda G factors for sulf-like and silicon-like atoms, like where the iron 13 is one such silicon-like atom. And the results were pretty good. If you take, I'm going back a slide. If you take the 1079 line, which has a triplet P2 to a triplet P1 transition, its Lambda G factor is 1.5. It's the same as the Lambda G factor of the base transition, which is triplet P1 to triplet P0. And this is the actual source of the degeneracy. But the large-scale calculations showed that the Lambda factor in the 1079 lines, so the triplet P2 to triplet P1 transition, deviates from the LS assumption. So this will break the degeneracy by itself. Although there will be problems with evaluating that sine square of theta b angles with very small quantities, but that's numerics, not a fundamental problem. And a second approach that we pursued was to revisit the whole problem and see if we can improve the inversion, such an inversion, in order to avoid the problem entirely. And what we found out is that the observation geometry proved crucial. If we, instead of relying on purely analytical calculations, we use a database of synthetic profiles which have access to more intrinsic information than, and fit that database of profiles to an observation, we will have access to more intrinsic information than what a purely analytical inversion can do. And one of these parameters is the atomic alignment sigma to zero factor that I mentioned in the beginning. And the atomic alignment will help break degeneracy, and it will also help us to pinpoint the source of a dominating emission structure along the line of sight. And I'll get to that right on the next slide. And the last point here is we advise that using lines of the same ion is most desirable, as this would let us to avoid calculating the dynamical ratios of abundances in maybe in erupting plasma and so on, which will prove very problematic. So the best possible choice is for a magnetic inversion is to use the iron 13, 1074 and 1079 line. And the whole problem arises from the fact that the information recovered from just one set of Stokes profiles in one line is insufficient to fully describe a full vector magnetic field. So we always need two lines. And I should have started with that, sorry. Okay, so more results of these experiments can be found in the papers led by Sasha Schiffman and Phil. And now, let's look at these geometries. If we look at in the plot to the left here, we have 2 points in the corona which are labeled P and Q. These are at a radius outward from the limb, and both have the same radius. These, in terms of the statistical equilibrium, are pretty much the same in terms of the anisotropy that is applied to them. So we use this analogy to first try to reduce the magnitude that such a database calculation will require. So what I'm trying to say here is that the information in point P and Q is equivalent in terms of polarization, with the note that the Q and the U components of Stokes will need to be subjected to a rotation along the line of sight and be brought to the same coordinates of P, while I and V are invariant here. And so you can take any point basically along a corona at a certain radius, rotate the QNU profiles to a reference direction where you build a database, and then compute your inversion, and then rotate the output products back to their original status. And another simplification that we could employ was to compute the database using only field strengths of 1 Gauss. And since the total the sum counts over a Stokes V line is should be linearly proportional to the magnetic field strength, we can just scale the Stokes V database value that we get for a 1 Gauss calculation with the observation, and then compute the actual magnetic field strength from that ratio. And this allows us to reduce one dimension of calculations needed in such a database. Okay, and on the right side, we see a plot showing a vector magnetic field component projected along the line of sight, and we see a degeneracy in action. So this theta B angle that we can recover will be degenerate in sets of 4. If we apply some gimmicks, and we will see how to do that, we can remove 2 of them, but we'll still have a solution that's degenerate in terms of in 2 positions along the line of sight. So normally you take the sign of the magnetic field strength, and then you know if it's the rightmost theta B's that are degenerate or the leftmost theta B's based on the plus minus B. And so all the solutions that we can get will still have this inherent degeneracy. And this is very similar to but not identical to the azimuthal degeneracy in photospheric inversions. It's just that it's not at a fixed angle. Now, another thing used to simplify our calculations was to take an observation. Let's say we have some region that we want to observe between 1 and 1.5 solar radii, and then we can split the database into individual calculations for simple specific heights. So, for example, in order to not load all the height information at one time and completely kill a calculation. So basically, you take the height, you feed the closest matching database entry, and then you pick just the y position that are equivalent to your observation, and that are most closely matching your observed height. This again relates to the anisotropy. So you have an alignment that is dependent on height. Okay, a few words on densities. I'm not even going to enter on the discussion of computing density ratios for different ions, which is completely non-trivial, and I'm just going to focus on the iron-13 line pairs. And we will see that theoretical calculation of line ratios, and I could only find very old papers describing the iron-13 case, recover a pretty narrow range with respect to coronal emission. So if we use these curves from this plot, before the whole calibration curves become flattened out and not usable, we can get up to most 10⁸ centimeter per centimeter cube, which is okay, but not ideal. Chianti, on the other hand, has more updated information. And so we computed our densities using 2 methods. One, in the statistical equilibrium and in the line formation process, density is a vital parameter. So we needed to include the density estimation in the actual database. So each database entry has a correspondent densities. So we just took a radial density profile from Allen, and then we just interpolate, we just added at each specific base coronal densities, we added an iterable ranges of multiplies and divisions of that number. So we get a reasonable range spread over 2 orders of magnitude in density, which we can iterate for an individual structure while still keeping a coronal base. And alternatively, we can use Chianti and just map grids of Stokes I ratio sensitivities at some several dozen heights between 1 and 1.5 solar radius. And these two things prove to be not really equivalent, but compatible in terms. And here on the bottom plot, you can just see the simple Chianti-Stokes ratio applied to a comp observation. And it's pretty trivial to do, I would say. Okay, then again, reiterating, what is this atomic database? We need to solve over a very large parameter space of 10 variables. We need to probe the full 3D space of X, Y, Z components. We need temperatures, densities, abundances, magnetic field strengths, magnetic azimuths, magnetic inclinations, velocity fields, and non-thermal broadenings. All are simplifications, and most of them that I discussed earlier allowed us to reduce those calculations to just a dimension along the line of sight. So along the x-axis, along the densities, and along 2 intrinsic magnetic fields angles, which correspond to the inclination and azimuth in the observer's frame. And the table just shows an example of a configuration of a database where this database has a set of 81 height entries. And you, for example, can see that the density just starts from a base coronal density at each specific height, and then it's multiplied with factors ranging from 0.01 to 200. Then the y-axis is just from outwards, eastwards or westwards, outwards from 1 solar radius, and in this case to 1.25 solar radius. And we took 60 line of sight position points where to interpolate between minus 1.5 solar radii and 1.5 solar radii. And the angles just follow a spherical convention. One goes from 0 to 2 pi, one goes from 0 to pi with a resolution of 2 degrees. Okay. And this whole database is synthesized with the CLE code, which is a spectral synthesis code developed by Phil Judge and Roberto Cassini. More recently, there's a new code named PikeHelp, which is developed by Tom Shad and Gabi Dima. And at some point, we will try to study the synergies between these two and possible differences in interpretations and how a database would look with CLE versus PikeHelp and so on. Now, this is, I won't spend much on this. So this is a simplified scheme of the whole inversion with all the programming and code modules listed. And what it does is, first, a user needs to manually build a database based on his observational constraints or hers. Secondly, the Stokes profiles and all the information will be pre-processed, correct database matches will be found, and so on. And based on the user's choice of wanting a 1-line or 2-line inversions, they will get spectroscopy products, and in the 1-line case, they will get a line of sight magnetic field inversion, and in the 2-line version, they will get a full vector magnetic field inversion. And these are the detailed modules for each of the 3 main steps. And I'm not gonna spend time on them. I'm just gonna leave them here in case someone wants to look at the presentation later on. Okay, so what do we get out at the end from this whole inversion? So in terms of spectroscopy, we get the line core intensity and background counts in all 4 Stokes profiles, corrected Doppler shifts, total line width, non-thermal line width, the linear degree polarization, and the total degree of polarization. In the case of one-line observations, the user will get B-loss magnetic field, which is based on the analytical approximation of Gaby-Dima. And we can also deliver the magnetic field azimuth angle from the arctangent of linear polarization, which we do. And then in the case of two-line observations, a user will get a full vector magnetic field with magnetic field strength, a line of sight component, the position of the dominating emitting structure along the line of sight, the plasma density, and the field strength together with the two angles can be also projected to a Cartesian plane. And the whole inversion in both mathematicals and code-wise terms has just been accepted, and you can find it online in this paper. Okay, now let's play with some actual plots. This is one simple experiment. So I just hung up 5 dipoles. So I just simulated 5 dipolar structures by just solving Maxwell equations, and I just hang them to fly freely through the corona. This is not in any sense a real observation and has nothing to do with reality. So what you see in a Stokes IQUV profile is this. You see 3 elongated structures here. I also degraded them a lot with resolution, so they're harder to actually recover. And you see these 4 structures, although they're 5. And this is your plane of the sky standard picture. What you don't see is, if you look from the ecliptic plane, the structure that's here below is actually 2 confounded structures along the line of sight. And they're just one behind the other. So in total, there are 5, and the 3 of them have 3 different height positions when compared to the limb, and the 2 below have the same position, just different orientations along the line of sight. And what do we get out of it? What we get is that we correctly recover the line of sight position of each of the 3 structures that were just floating by themselves along a line of sight. And this is important. So, and this is the main assumption on such single point inversions. You need to have only one dominating structures along the line of sight for it to work. For the 2 confounded structures, the inversion just failed. And here you can see a similar information, but in a graph format, where we just anchored one structure behind your line of sight at -2 solar radii, and then we put the 10 structures at varying heights. And what the plots show you with the chi-squared and density plots that you see here is that they're monotonically increasing with the height between the 2 sources. So what does that mean? If we put another structure just next to the original structure at -2 solar radii behind the line of sight, it will recover reasonable information with reasonable metrics. For structures that are similar to that, so for example, at 1.8 solar radius behind, again, it might work. Then everything starts to fall down as these 2 confounded structures are farther and farther away, because the resulting Stokes light that comes is not compatible anymore with one single point observation. So this is the main caveat of such inversions. Another test is a simplified fake observation using 3 large-scale dipoles. And again, you can see a plane of the sky standard corona with a occulted disk, and you see 4 loop-like structures hanging around here. And this is because one of those dipoles has a double loop structure. And all of them have different thermal properties, and different line of sight speeds and different turbulence speeds. Again, if viewed from the ecliptic, that is from the North Pole down, these structures do not touch each other. So they're completely separated along your line of sight, though they appear to be a very simplified active region in this simulation case. But they have absolutely no connection between them in terms of your line of sight integration. Okay, so what do we see? In terms of spectroscopy, we even see some structure which I labeled here as C for a current sheet, because I arranged those line of sight, those loop structures for two of them to appear in the integration as coming from the same thing. And you see a small semblance of a current sheet. That's completely fake. And here you see Stokes profiles in that current sheet. And what I wanted to show here mostly was how bad a Stokes signal can get when you have multiple confounding structures along the line of sight. And this, coupled with the previous experiment, might prove very problematic for these types of inversions. So I'm gonna start a project with Caitlin in a couple of weeks. She will be our new REU student, and her main job will be to take a profile like this in the like these black curves show, and try to use either statistical or machine learning techniques to actually recover the contributing Gaussian-like profiles that give this this very convoluted Stokes signal. If we can do this, we can do the same thing for the full Stokes IQ UV observation, and then we may actually be able to invert each of the components separately, and then sort them out along the line of sight and produce an inversion in a 3D-like cube. But we'll see how the project evolves and if this is feasible. And I'm really excited to start working with Caitlin. Okay. Now, again, this is an example of a single point solution. And this is just one, I think it's also the 1 point, I think it's also that current sheet point that I took. And then you see the inversion products that come out of it. And the main important thing to note here, the inversion algorithm will sort out database solutions which most closely match your observation. But what you see here is that the degeneracy that comes in pairs of two. So you get similar densities. The height is fixed. It's an input parameter. But the depth along the line of sight is symmetrical to the plane of the sky. So you either see the structure as coming from behind the line of sight at a certain angle, or in front of the line of sight at a certain angle, but you don't know which is which. And this is an intrinsic degeneracy in solving this problem. And now on top of that, and this translates to the azimuthal and line of sight angles, which one set is supplementary and the other set is no. One set is supplementary and one set adds to 360 degrees. And then those again will translate if you perform a Cartesian transformation in the actual BX, BY, BZ components. Now, because of these degeneracies, we found out that since we are not actually including multiple B field values in the database, we can split our chi-squared calculations for sorting out the solution into an IQU component and a V component. Because IQU can directly match the observations, because that's what the database is built for, but V can never match it, can only match the observation when the observation field strength is 1 Gauss. So you will always get a residual chi-squared. So we separated this solution, and in order to further look at these, at the quality of the inverted parameters and degeneracy. And one thing that we found is that the user will need to match the database resolution to be compatible with the noise influence in an observation. Because if you look here, these chi-squares are very overdetermined. And this is simply because the database resolution is so high that you basically get just very similar solutions with just plus minus 2 degrees in variance in angles around the correct observed value, because you cannot disentangle the observed Stokes profiles to a resolution finer than the 2 degrees used here. So in this case, a coarser database would have been better and you would actually get different solutions that are compatible with your observation instead of getting very overdetermined sets of the same thing. Okay. And this is how, I'm not going to spend that much on it. This is how a typical inversion output looks like. For that free dipole simulation, this is the spectroscopy product. And we have a wavelength Doppler shift and the backgrounds and line cores in all the Stokes I background and the line core components in Stokes I, Q, U, and V. And full width half maximum of the line, the non-thermal width, assuming we would know what the instrumental broadening function is. We don't know yet, but assuming that will be something that we know about, and the linear polarization and total polarization fraction. Now, in terms of if the user desires only a one-line inversion, we use the corrected magnetograph formula that Gabi Dima developed, along with the classic magnetograph formulation. So what does this do? So because of that F factor that I mentioned earlier and the degeneracy, this B-loss observation will split the solution into two branches, which are both symmetric to the classical magnetograph formulation. I couldn't make the resolution for this to be really clear. So the counts in the first degenerate solution are lower than the classic magnetograph solution, which are lower than the second degenerate solution. And Gabi Dima showed here that one of these two solutions will almost perfectly match an observation, while the other will fail. And with the classical magnetograph solution sitting in the middle of these two solutions. So we chose to implement this analytical expression. Now, in the case of two lines, we get to the nice parts. And the main products are the database entry that was matched, the chi-squared fit residual, a measure of the plasma density, and you see that it's very noisy. The computed observed height, again, is more or less of an input. And here you see the degeneracy between the first and second solution, for example. So the first solution will bring you mostly all the components that are behind the line of sight with a set of magnetic field angles. And the second solution will bring the same magnetic field angles, but in front of your line of sight. And this is the line of sight position that's derived. And then you get the magnetic field components. But better than seeing them here, let's look at them here. And what we have here is column-wise, we have an input CLE atmosphere, which was that free dipole simulations in terms of BX, BY, BZ. And you see that in this case, BX kind of vanishes. This is the zeroth solution from CLEDB, from the inversion. And you see how noisy and it is. This is a best solution that's not achievable in reality, where we computed the minimal difference between the two solutions and the ground truth, just to see that we are indeed recovering what we should be recovering. So this is this panel here. So column 2, row 3 shows you how an observation will actually look like if it's really degenerate along the line of sight. So a separate inversion like the disambiguation used for HMI for photospheric magnetic fields will need to be employed here in order to fully resolve this problem. And here is a metric of the difference between the best solution and the actual ground truth, where mostly the histograms show that for BX, BY, and BZ, 85% of the profiles have a deviation of maximum 20% from the ground truth. And in the case of BX, something happened which is not yet elucidated, where instead of the field strengths canceling out, the database summed them. So instead of getting a canceling out contribution, you got a double contribution in BX. And this is also what the difference say, that most of the pixels just fall into a 100% difference from the ground truth, which is double. Okay. Moving to this. So what we found out with this work and these experiments is that it was really important to estimate the line of sight locations of the emitting plasma in order to resolve as much degeneracies as we could. And if we don't solve for the alignment and the line of sight, we get a solution that's 4 times degenerate instead of 2 times degenerate. So that's bad. And what we want to do is study if we can distinguish multiple emission regions along the line of sight. If we can safely combine lines from multiple atoms, which will prove problematic. Study synergies with what PyCal can do for us. An eventual disambiguation for the full coronal vector magnetograms will need to be produced. And of course, the most important part is actually applying this inversion to UComp and DKIS to produce science. Now, actually, I haven't finished. I'm going to open up a can of worms. And please take everything that I say from now on with extreme uncertainty and skepticism. Since there is no data with either with UComp or DKIS, and Stokes V really doesn't exist as a measured quantity in observations, I try to see where and how we can derive an equivalent information that would be encompassed in a Stokes V measurement and independently supply to the inversion to see if we can get an interesting output. So for this, we took these I followed the work of Zihao Yang, and which again builds up on work by Steve Tomczyk, Morton, and so on. And I just found the public repository of comp observation of level 2 calibrated comp data from Yang's paper. And I just picked one data set pretty much at random. And that date was in the beginning of the data set somewhere, and it was 27 March 2012. And I just plotted the Stokes IQU information for the 2 iron 13 coronal lines. There is no Stokes V information. So this is a big question mark. So what can we do with this? Well, following the work of Zihao Yang, we can provide an estimate of using coronal seismology with comp and provide an estimate of a field strength and its plane of the sky component. Okay, so these plots just show that comp observation with Doppler velocities, line widths, plasma densities, and the phase speed computed from the Doppler speed. I am really grateful for the authors of the Yang paper for freely giving up their codes and methods. I have implemented most of them in Python myself, but I haven't finished, and I didn't trust what I was doing by today to actually produce those things. So these are produced with the IDL codes of Robert Morton, if I remember correctly. And this is the phase speed. This is the phase angle, which can be used as a proxy of the magnetic azimuth. And this is the classical azimuth angle computed with from polarization from the arctan of Stokes Q over U over Q, half arctan of Stokes U over Q. Okay. And using this technique, you can get magnetic field strength from the Doppler oscillations. You can get a plane of the sky component, and you can compute that either with the phase angle from the Doppler oscillations or with the azimuth angle. And in this case, one important thing was that the phase angle at lower heights is more fine and reliable than the arctan of the linear polarization. But this is also because of whatever counts we had in Stokes Q and U for 1079. So with better counts, I don't know how these two will compare. So these plots have the same scaling in all 6 panels. And I wanted to show how few counts you actually get in the linear polarization in 1079. So you get this. Then you can feed this to CLEDB. So what do we need to feed to CLEDB to get the equivalent information of a Stokes V line measurement? We need the magnetic field strength, which we have. So the B field strength is just a proxy from it's the same thing, it's just a different color scale, sorry, from the Doppler oscillations. And you can then take the sign of the plane of the sky component of the magnetic field and assume that's the sign of the magnetic field. And this is a big assumption, but it's the best we can do. And it makes sense to some extent because that angle will vary by 0 to 2 pi. So you should get the whole range of available angles. You feed that angle, you run an inversion. The residual seems to be low exactly in regions where you had strong polarization signal. You find line of sight positions which were really nicely put right on the plane of the sky in most regions close to the solar limb, which was again a good indicator. And you get the field strength that you get is the field strength that you put in. This is not an actual inversion project, it's just plugged in there. And then you get the phi B and theta B angles of the magnetic field. Now, what do we do with them? We can get from Stokes IQU only magnetometry a full vector magnetic field map of the corona. And you have a BX, BY, BZ component of these fields. On a first glance, you will see that the BX and BY look oddly similar, but that is not really the case. So in this bottom left plot, I plotted the difference between BX, BY, and you can see that in different places, so the signs flip between them. In select places, the intensities are completely different in the two components, but they have this structure. And we were left to figure out what does this mean? And this might mean it's just an interpretation of the actual sun at that day in terms of global magnetic fields. Remember that COMP only has a 9 arcsecond resolution. So what you see here is basically a large-scale dipole between the two hemispheres where you have two very active region conduction bands. So in this case, it seems that indeed these components make sense. And if we look more at a simple extrapolation, so I didn't even produce these plots, I just took them from the sun today of how the sun looked at that day. And you can see that you have very large scale dipoles that are corresponding with your X and Y solutions. So X means a field coming slightly towards you or going away from you, and Y means a field that's radial and radial with a sign or no radial component. So what you see is a strong radial component, which might be equivalent to the extrapolation. and that field is also inclined and coming towards you and closes back down around here. And the same analogy can be done on the other hemisphere. Now, let's look more at this. So those were global maps, but if we look at actual zoom-ins, we can see that in the eastern hemisphere, we can recover information about a very nice active region with high coronal loops. And in the west, we see those big global scale fields. And for example, you can see here in this point, I hope you can see my cursor. You see here that this has a strong BX component. So this is very inclined, while it's not one-to-one to what's in the radial component. So the maps, even if globally they look very similar in terms of the line of sight, they are different. So I hope you saw all the worms running around. So please take everything with a grain of salt. All of these things are in a very prototype version. And there are caveats to this. So in order to properly build the phase speed, you need roughly an hour of observation. So such a product will not be suited for fast dynamics and so on. And it also relies on the propagation of Alfvénic waves, most probably kink waves that go radially through magnetic structures. And in the cases where you have erupting structures or high turbulence, those waves might be dampened and so on. So again, this might work well for a synoptic-like program or a synoptic-like inversion, but it doesn't have the power to recover fast dynamics. That's what I'm trying to say. And what the main, I didn't show yet uncertainties because these are not yet finalized, but most of them are in the order of 20%, maybe 25%, but they're not fully evaluated and also double-checked by an independent eye. It's the same thing with all the products. So I don't trust myself that I didn't wrongly take the orientation of an angle in the other way around. So this will need to be fact-checked by someone else. And then I will include this whole branch in CLEDB in the public repository. But the main and exciting information is that COMP datasets might actually contain untapped information regarding the real coronal magnetic field with all its components. And this is something that excites me a lot. And that's it. And thank you. And I hope I wasn't too confusing.
No, thank you very much, Alin. Let's go to questions. I know it's a little late. Any of you that have to leave at 3 p.m. Mountain time, please do so. But who has questions for Alin? I see Ryan has raised a hand. Go ahead, Ryan.
Yeah, great talk. So I was kind of curious about, you showed earlier the different components of the IQ, U, and V and how they sum up. I was just wondering, like, how, I get that you can try to disentangle this observed profile in this Stokes component is probably made of these different simpler components, but how do you consistently disentangle and associate, okay, this component in Stokes I corresponds to this component in Stokes Q and this one in U and V? How do you do that?
So stop me if I didn't understand your question right, but The answer would be we don't use the raw profiles. So when looking at the degeneracy of the problem, we could eliminate one measurement, which was the measurement of Stokes I in 1074 and norm around it. So you get a vector of 8 integrated profiles where the Stokes I in 1074 is always 1. And then you just get the ratio of I to Q, I to U, I to V, I to I2, I to U2, I to Q2, I to V2. And you get this vector and you compare it with an equivalent vector from the database. And we did this because we cannot really evaluate the we cannot get polarimetric what's the name? Sorry. We cannot polarimetrically calibrate these things to use raw counts in intensity. So instead of using the raw counts, we just match the vector of ratios between the components. So you get one vector of 8 elements for one voxel, for one pixel of observation, and then you match it against let's say 100 million database entries that are correspondent with that observation. And then you just rank the database solutions, and then you look at the physics of the best matching solution. It's the degenerate branch, and then second best matching is the degenerate solution, and so on.
Okay, so you're saying that like my question was more about so I get what you're saying with the we're just measuring these polarizations with respect to I get that. My question was more like how you go from say a blend of 3 Q components and a blend of 3 U components. How do you associate each of the components of those different polarizations?
Bits, right?
Yeah. So how do you associate?
It's exactly what I said. We can't do this right now.
Okay.
The main assumption around this is that there's only one component. That's all we can do. Caitlin will try to work on disentangling these things. And so basically what the RU project will be about will be taking this, let's say, black curves of Stokes I and providing a set of 3 or 4 or however many there are individual Gaussian-like components that comprises that very non-Gaussian profile-like. So for the moment, the inversion, if it picks that the profile deviates a long way from a normal distribution, it just says that pixel is bad and neglects it. So that's the current implementation in it. In the future, I hope we will be able to overcome even this, but it's not currently there. Am I making sense?
I guess so, yeah. Yeah,
for example, with the comp resolution, I was expecting it didn't prove to be, everything seemed reasonable, but as you go along and increase in resolution, I don't know what will happen. So hopefully you will get decent results in a majority of the voxels.
Okay, so this is so what you're showing here with these multiple components contributing to a very complicated profile, that's more of an edge case that you might expect in, say, a few % of all your pixels, right?
Hopefully. We don't know because the observations don't exist. But
we'll have to see what DKIST.
Yes, that's what DKIST will do. But again, you also have a cross section of polarization light coming to you. So most of the things should be close to the plane of the sky if we interpret things correctly. Because if it's farther away from the plane of the sky, the cross section of that of the light coming to you towards your detector will be very small, so that signal will not be dominant, or maybe it will even be not significant in your total counts.
Cool, thanks.
Right, Sarah.
Okay, I have lots of questions, but we're going to have to follow up later. Really, really interesting stuff, Alan. I actually love the can of worms stuff. I want to talk to you more about it. I just wanted to clarify one point, which is, am I correct that in your database, you're effectively evaluating at a point, at a given distance and a given density and a given magnetic orientation? Is that right, along the line of sight? So you're kind of doing a point solution, is that right?
Yes, it's a single point inversion.
Okay. Have you considered doing a database, expanding your database to include profiles of some sort? And maybe we can talk more about it, but what I mean is that there's a lot in the corona which is going to be kind of a much more smoothly varying magnetic structure. You know, think of a smooth dipole, for example. And I know that there's a localization to the plane of the sky up to a point, but it can be complicated. So like if you have you considered imposing an assumption about the gross properties of the magnetic structure and then having iteration on that to create your database?
Not because how I see it is a two-step process. So you do this matching, and then I think if you impose such a constraint, you will be able to. So, for example, the simplest such constraint that I can think is just to impose a diff b equals 0 and see where you get. And if you impose such a constraint, then on the map, after you get a set of solutions, and then you pick the solution that's best to the constraint, is the way that we thought of doing it.
Very cool. I'll follow up with some more later, but this is great stuff.
Thank you.
All right, I don't see any other hands raised, and we're way past the hour. So I want to thank Aline again for a wonderful talk. And I think I'll see you all guys next week, I guess. I don't know the colloquium schedule, sorry. But thanks for coming. See you soon.